This conference will now be recorded.
And then I will start with a proper introduction of the work that we have performed. Then we will establish some objectives. After that, we will follow with materials and methodology. After that, we will have a deep insight in the results and discussion section, and finally the conclusion. Well, let's start with the introduction. As I told you, I'm Antonio. I work as a PhD student in the University of Huelva, that is located in southwest Spain. We can see a picture of our group. As you can see, we are a big group of people. We are focused on bitumen, lubricating greases, high pressure fluids, but we all have a common nexus. We are experts, or at least we try to know a lot about the rheology of these systems. That's our building, the engineering school, and as there is where we have our offices and our laboratories. And we have a research center that is called Prodostex. Well, but this just hasn't been done completely in the University of Huelva because it's the product of an internship that I did in the Aalto University, located in Espoo in Finland, under the supervision of Orlando Rojas, just next to me in the picture. And these are just a picture of the facilities that we have there in the university. Just part of the facilities. It's a really big university. Well, now let's start with the proper introduction of the work that we have done. Our work is centered in oil structuring. Oil structuring traditionally have been done, for example, in the food industry by using triacylglycerols. This is a problem because triacylglycerols are strongly correlated with obesity. On the other hand, for example, in the lubricant industry, oil structure has been also tried, and they have been doing this by using metallic-based soaps traditionally. However, these metallic-based soaps and the use of synthetic and mineral oil finally get to environmental problems, and they put into danger the sea life and our human health after all. So are there any alternatives to oil structure? Of course, there are. If you take a look into literature, for example, for the food industry, you can find that cellulose derivatives, natural oxides, silica nanoparticles, and glycerols can play a very good role in food industry to structure the oils. On the other hand, in our research center, we have tried for almost more than a decade to try to focus on the lubricant industry and try to find a different solution to those metallic-based soaps. And for that, we have used also cellulose derivatives, but also chitosan and residual straws. However, in this job, we haven't used any of those. We have used a completely different biopolymer coming from the cellulose pulp biorefinery, that is lignin. Why have we used lignin? Because it's a really low-cost biopolymer that is almost in its totality just burned to recover some of the energy spent in the process, and that it has really good inherent properties like an aromatic structure and inherent antimicrobial properties. So we have selected lignin as the biopolymer to thicken oil. Well, what about lubricating greases? Can we obtain a lubricating grease just by mixing an oil and a biopolymer? The answer, unfortunately, is not. We can obtain a proper grease just by mixing the oil and the biopolymer. What we get is just some systems that are separated. So recently, or in the last decades, we have been focused on using isocyanate and epoxy compounds to try to cross-link both the oil and the biopolymer. However, we have obtained really good system with really good stability. We have obtained really good rheological and tribological properties, but we are using systems that isocyanate and epoxy compounds that are not good for the environment. So we are also endangering the sea life and rivers and oceans. So we need to find another approach to try to eliminate those cross-linkers and create more fully renewable oil gas. And for that, we focus on the on the modification of the biopolymer. And that modification of the biopolymer we did by acetylation. With the acetylation, we increase the compatibility between the oil and the acetylated lignin. Why? Because now they are more hydrophobic, both of them, so they can compatibilize better. And moreover, we eliminate the use of hazardous cross-linkers. So in this system, everything is completely renewable, and we can create systems that are harmless to the environment. Well, so let's now establish the objectives. The first of them, I guess you already have imagined it, that is to structure oil by mixing with acetylated lignin. And the second of the objective is to try to study different degrees of acetylation and how they affect the mixture. Well, let's now pass to the materials and methodology section. Well, first of all, we have tried indolent AT as the lignin benchmark, castor oil as oil media, and acetic anhydride. We have used other components, but these are the main components in our study, and we don't want to mention all of them, just you will see them when the proper time arrives. Well, for the lignin acetylation, we have chosen two different paths. The first path is the one that you can see at the bottom. We have called it traditional chemical lignin acetylation, and it's just the mix between lignin and acetic anhydride and pyridine in 1:1 volume ratio. This is how lignin acetylation has been commonly done. And in this case, we have selected 48 hours and 25 degrees as the time and temperature of the acetylation. You can see in literature a lot of different times and temperature, but generally what we want is to try to give the time enough to get the most acetylated lignin possible by this pathway. On the other hand, we have tried another completely different lignin acetylation, that is by the use of microwave power. With the use of microwave power, what we can do also is eliminate pyridine, that is a very harmful solvent. So just by the means of lignin and acetic anhydride, we can obtain acetylated lignin. And in fact, we can obtain acetylated lignin in much less reduced processing time. As you can see here, we only needed 10 minutes to get very good acetylation conditions. To try the different degrees of acetylation, we tried from 130 to 160 degrees acetylation temperature. Well, just for the performance of the ologels with lubricating resist properties, we just mix the acetylated lignin and the castor oil. Before 30% acetylated lignin content, we obtain some separation. So we selected 30% acetylated lignin content for the performance of the gels. And the performance was just done by intense stirring for 3 hours. And you can see this is the product that we obtained after that ologel formation. Well, for the characterization, we have performed both phosphorus and hydrogen MMR. We have also performed thermodynamic analysis from room temperature to 600 degrees. We have also performed Fourier transform infrared spectroscopy from 400 to 4000 wave number with a resolution of 4 inverse centimeters. And we have performed different types of imaging. Optical, as you can see on the right, also confocal. So for the confocal microscopy, we have dyed castor oil with Nile red. And finally, scanning electron microscopy by using the equipment that you can see in the image. And after that, we have characterized the ologel by performing rheological characterization by frequency sweeps and viscous flow measurement, both of them from 0.03 to 100 radian per second and inverse second respectively. Well, let's now start with the results and discussion. Well, first of all, I would like to show you the phosphorus NMR results. As you can see, the indolent AT has very high hydroxyl groups. So after the acetylation by microwave assisted acetylation, we can see that as we increase the temperature, we obtain less and less hydroxyl groups. In both cases, both for phenolic and aliphatic hydroxyl groups. So finally, having the same response in the total hydroxyl groups behavior. And finally, we are having a higher degree of substitution as a consequence of that elimination of hydroxyl groups. But it's also worth mentioning that finally, with the traditional acetylated lignin, we obtain the lowest phenolic, aliphatic, and finally the higher degree of substitution of these hydroxyl groups. By hydrogen MMR, we can quantify how many of these systems have been transformed into acetyl groups. So we can see for the phenolic acetyl groups, again, as we increase the temperature, we obtain higher quantity of these acetyl groups formed, in the inverse case of what happened with the hydroxyl groups. However, for the aliphatic acetyl groups, what was happening is that from 130 to 140, we're having a high increase of these acetyl groups, But from 140 to 160, those values are more or less constant. Finally, again, it is worth mentioning that the traditional acetylated lignin is the one that shows the highest phenolic and aliphatic acetyl groups concentration. So after this, we wanted to see, can we get a correlation between the hydroxyl group loss and the acetyl group formation with the processing temperature? And in fact, we can obtain that. We can see that we obtain almost a linear trend between that relationship between hydroxyl and acetyl groups and the processing temperature. So the first of our big outcomes of this study is that we can tune the acetylation process just by changing the processing temperature. Well, let's continue with the thermodynamic analysis. As we can see here, the indolent AT lignin is the one that shows the highest residue, or let's say the highest resistance to temperature. And then as we increase the acetylation temperature, we increase the weight loss at the main event. So finally getting a lower residue. So we are at some point, consequent of the severe conditions that we are applying, we are making easier that this system get how to say eliminated by the temperature. So it's easier to degrade. Sorry, degrade was the word. It's easier to degrade our system consequent of the severe condition applied. Well, about the FTIR results, we can see on the left that the indolent AT again shows a really high hydroxyl groups concentration. The conventional acetylated lignin shows almost no acetyl groups. And for the different temperatures, as we increase the acetylation temperature, we obtain again lower hydroxyl groups. That's just confirming what we saw in the MMR results. However, in this FTIR, we can also see that we are having a displacement to higher wave numbers when this acetylation temperature is increasing. What's that telling us? That's telling us that we are losing some hydrogen bonding and structuration. So at that point, we can see that the formation of acetyl groups finally makes our acetylated lignin less structured, consequent of that acetyl group formation that just dampen the formation of hydrogen bonding. On the right, we can see several bands, and we can take a look on the carbonyl groups band that is increasing as a consequence of the same, the acetylation temperature. That was just what we were expecting, as a higher concentration of carbonyl groups, just meaning it's just a consequence of higher degree of substitution. Just again confirming what we saw in the MMR result. So let's now pass to the scanning electron microscopy. As we can see, for the indolent AT, we get porous structure with kind of spherical shape, and they are big clusters. But then when we pass to the microwave acetylated lignins, we can see that there are huge differences, as those microwave acetylated lignin have a very porous structure and non-spherical shape. While for the traditional acetylated lignin, we have spherical particles with no porosity. So by changing the processing protocol, we can obtain lignins that have very different surface appearance. That's also a really good outcome that we observe here in this study. And that surface difference will have a big income in the properties of the gels, as we will see. Well, so we have the acetylated lignin, and we have tried to mix it with different oils: sunflower oil, olive oil, and castor oil. And what happens is that when we mix the acetylated lignin with sunflower oil and olive oil, we get unstable systems. But when we mix it with castor oil, we get stable systems. So from now on, these properties of the gel are about acetylated lignin plus castor oil mixtures. And now we get the rheological results, both in the viscous flow measurement on the left and the viscoelastic function on the right of the acetylated lignin and castor oil mixtures. Let's go step by step, as you can, so you can see all the differences that we have observed. For example, for the system with 130 degrees, that is the one that shows the lowest acetylation degree, we can see that both viscoelastic function are quite close, the viscoelastic function are high, but both the storage moduli and the loss moduli are really close. Even we can see a crossover at low frequencies around 2 radians per second. So that's telling us that we are having not really a well compatibilized system, but kind of a colloidal dispersion, just probably as a consequence of that low degree of acetylation that doesn't provide a good compatibilization between the two systems. And also that's rising the viscose values. As we pass from 130 to 140, that is a much higher acetylated sample, we can see that we obtain more or less the same storage modulus, but reduce loss modulus. So the relative elasticity has been increased. Also, we can see here a shift to higher frequencies of the crossover, and also we can see that we obtain lower viscous values for this sample. So finally, our system is getting more compatibilized, so the relative elasticity of the network is being increased, and all the viscoelastic function and the viscous value have been reduced. Well, again, the same more or less can be said for the 100 from the 140 to the 150 sample. Here, as we can see on the dark green dots, triangles, we can see that the storage modulus has reduced. The loss function has been even much more reduced. So again, the storage, the relative elasticity has been improved one more, and the crossover has been shifted again, even to higher wave numbers. So again, we are seeing the same. And also the shear thinning behavior, as you can see here, has been significantly increased, consequent also for higher entangled system. Finally, if we compare with the conventional acetylated lignin, we can see that the conventional acetylated lignin, as it shows the highest degree of compatibilization, the highest degree of substitution, finally gets the lower viscoelastic function, really high shear thinning behavior too. Nonetheless, it is worth mentioning that for the 160 degrees case, we obtain kind of a strange behavior. Why? First of all, we are obtaining really high viscoelastic function that was not expected. We are obtaining really high relative elasticity. That we were in fact expecting that. We obtain really high relative elasticity. In fact, the crossover is shifted to high wave number. Even within the frequency range that we cannot see any crossover. And the shear thinning behavior is the sharpest one of all of them. But the viscoelastic function are increased probably consequent of the severe conditions, because these severe conditions finally get also to a reduction in the particle size. So as we get higher contact area between the castor oil and the acetylated lignin, finally we can get higher structure network consequent of this reduction in particle size. So these both phenomena maybe take place in this system, and finally we can get higher viscoelastic function that we were not expecting in the first place. So just as a summary, just an increase in the acetylation temperature, increase the shear thinning behavior, reduce the particle size, increase the relative elasticity of the sample, and reduce generally, at least, the viscoelastic function. So we pass from colloid dispersion that are not so well structured to partially soluble systems that generate a really good system with a very good shear thinning behavior typical of commercial lubricating greases. So what's the comparison between commercial lubricating greases and this system that we have obtained? In fact, these rheological results and both the viscoelastic function and the viscous values highlight that they can be, this system can replace those lubricating greases, commercial lubricating greases, from low NLGI grade. So after that, as we wanted to try if with this acetylated lignin that was able to thicken the oil, to structure the oil, if we could use it in a completely different approach. That is the use of this acetylated lignin as a Pickering emulsifier. As lignin has been used quite a lot for oil in water emulsion. So what we tried in this study was to get at least some preliminary result of water in oil-based emulsions, as that one I show you here in this picture. As you can see, we can see that we have water droplets that are surrounded by that acetylated lignin for both the conventional acetylated lignin and the acetylated lignin obtained by microwave-assisted acetylation. We can see by the confocal microscopy that our continuous media is the castor oil, while the water droplets are just in black. So the continuous media is oil, and the water is just forming the emulsion. And finally, just to see some results, some rheological results of these emulsions, we can see that if we have no water, we have really low viscoelastic function and even an Newtonian behavior for the viscous values. While as we increase water, as we increase the content of water, we obtain higher both viscoelastic function and viscous values. We can add up to 30% of water, and the system is still stable. However, after we add 40%, finally we get two phases separated, so our emulsion is reverted. Well, finally, I wish just to read some of the conclusions that we have obtained. First of all, we have obtained a greener pathway to obtain fully renewable oil gels just by the combination of acetylated lignin and castor oil. So we did remove of those cross-linkers that were harmful beforehand. Well, again, just to highlight the process's significance, how the course of acetylation dramatically affects the properties of both the lignin and finally also of the dispersion obtained. About the viscoelastic function, just say that the rheological properties of this oil gel imitate fairly well those of the commercial lubricating greases of low NLGI grade. And finally, that this acetylated lignin can play a good role in emulsifying as emulsifiers because of the hydrophobic character that guarantees the stabilization of water in oil-based emulsion. Well, thank you all for your time. I will really pleased to answer any question.
Thank you for your presentation, Dr. Antonio.
Thanks.
So yeah, do we have any questions? Any questions for the presentation? I guess there are no questions anyways. Thanks a lot for your time and your presentation. It was informative. Thank you.
Thanks a lot.
Yeah. So moving on to our next presentation, we have Dr. Yabibal Getahun from Harbin Institute of Technology, China, on the topic mixed metallic oxide of iron, cobalt, and manganese applied to thermochemical solar energy. So, yes, Dr.
Okay.
Yabibal, you can just click on the screen button so that you'll be able to share your screen with us.
Can you see now?
Oh no, actually not yet. Maybe it just take 2 seconds of time difference. So yeah, we're not able to see it. Under the mic, camera, and
Okay.
screen, yeah, you can just click on screen button. You'll open a pop-up window to select the application that you would like to share with us.
Okay. What about now? I shared it.
Yeah, now it's visible.
Okay.
Yeah.
Okay. Do you hear me?
Yeah, we can hear you. Is it possible to just give it in the slideshow format so that the complete screen will be visible? Because I guess only half of the screen is being visible here. Yeah, you can just click on the slideshow, view slideshow. Yeah, it's perfect now.
Okay.
Yeah, it's perfect. We can continue with the presentation. Thank you.
Okay. Thank you. This is Yabubal Getaum from Harbin Science and Technology Institute, China. Well, the focus of the research is on mixed metallic oxide of the iron, cobalt, and manganese, which are applied for thermochemical solar energy storage application. So here is the context. We have introduction, literature review, obtained result, and conclusion. Actually, there is a gap on this. So from the introduction, we have the main application using the solar energy to apply on the reduction of the metallic oxide for energy application purpose. So overall, what is now the solar energy distribution and the concentration solar power CSP in the world today? As you see, now the increasing of this application of solar energy, the increasing installation capacities from year to year is increasing, and the distribution, you see in the first case, the distribution of the worldwide, the available solar energy along the globe. So in this region, we see that Africa is rich in solar energy distribution. So application of this energy in that area is really applicable and benefitable. Then the installation of CSP in the world is just increasing. So which means that now the people, these days, people are turned to apply solar energy. So among these, we have parabolic traps, Fresnel traps, solar tower, power dish, the distribution of the world, which is going to be in the market. So the application of this solar energy is a different application we have for power production, hydrogen, water pump, voltaics, solar cooker, heat residential home, solar fuel for vehicles, steam power generation, and solar heating. These are the application of for solar energy to be stored so that it will function for such a purpose that people are turned to be in the area and the sector. Well, the significant study of this important issue of this paper and the renewable source of energy is that the overall reduction of fossil fuel, which is sometimes fossil fuel exhaust, which will affect the environment, so as to reduce the impact of the fossil fuel. Now people toward this in the area of renewable solar energy, which it means that one of the focusing area is solar energy, which is highly available, especially places like or continents like Africa or places which are located along the equator regions, so where the sunshine is highly available. So this kind of energy is very good in that area. So what is important? Solar energy is, we know all now, sustainable, which is low cost. Improving the thermal performance of solar energy storage reactor is another issue that people are doing. Based on the challenge, the opportunity, researchers what are doing today, which is just one thing they are working on the thermal performance of reactors. The others are how this energy is stored so that like metallic oxide to be reduced, which later function for many other things. So in this significant study, we see these are many things to be observed. Which are already done as the researches are just how this concentration of solar energy reaches the reactor so that it will function for utility for power energy demand purpose. Here are different researchers purposely performed how solar energies come from the sun and how it reflected back and then how it is stored, how it transfers, how the outlet temperature would be. This is overall how people are doing for energy storage application for solar radiation. So these are the obtained results, thermal performance analysis for mixed oxide and chemical energy. So this is the main topic, what we have done in this research. Now the purpose is just applying temperature to from room temperature to 144 degree, and then when we apply this, we have done this for different oxide proportion. First, what we checked is just manganese, cobalt with different proportion. We analyzed under thermographic analysis, and then after we got a result for this manganese and oxide, we select a good proportional for stability, cyclic stability, and then we added iron at last. The main purpose is that which part of composition for iron manganese oxide is important, which later to develop for energy storage application. So we have done for different proportion. For example, 25% of manganese, 75% of cobalt, 50-50%, 20-75%, 70-25%. So totally we have checked for 6 proportion. And then lastly, we got for this 50-50, and then we add iron. So we'll continue with that result. Okay. Graphic analysis for the composition of the oxides. So we see that in the first for 2 cyclic redox reaction has gone. So as you see that in the first stage, we see that evaporation. In the second stage is decomposition starts, and then reoxidation as this stage 3 is ongoing. So stage 4 once again, then decomposition happen. So the situation ran for 2 cyclic redox reaction, and then among these, which is going to be more stable. So this is a situation how we which proportion of metallic oxide is important for cyclic stability, so that for further study. Well, this is the weight reduction with time for the pure oxides, cobalt oxide, iron oxide, and manganese oxide. So we checked for pure oxide. In this case, for the first cyclic redox reaction, we analyzed that for all six composition, and then for first charging process. So from this, we see that for different, for example, cobalt, we see cobalt from charging from room temperature to 1400, then we see the single decomposition there. So in cobalt oxide, from this region, that the iron takes for it is exchange, it just goes straight. It needs high temperature to change its phase. Whereas in the first case, most of the composition in this area, just evaporation starts, it shows, and the second stage in this area, decomposition, and then a plateau here, just more than 1000 degrees centigrade is a plateau is coming. This is a decomposition, this is evaporation area. But iron continues constantly without losing its weight. Only just more than 1200 degrees centigrade that iron started to decompose. Okay, here we see that for different composition for pure oxide, still for manganese oxide, we see that multi-decomposition here. The 25/75 composition is just multi-decomposition. And then this is a mixed oxide. So we see that in the 25%, 70, 25%, and 55%, in the 50 composition of cobalt, almost this normal situation happened in the thermographic analysis. Okay. The other is a weight derivative graph. When we see the weight derivative graphs, we see that phase changes happen. At what temperature these phase changes occur? We see that most of the phase changes occur for this composition. It's about 40 to 500 degrees centigrade in the first case, but we don't know exactly. It has to be further tested at what temperature. Really, this temperature is the phase changing. It needs to be exact test that we'll do sometimes later. Anyways, from this weight derivative, we see that the phase changing temperature, but these phase changing these phase changing temperatures are real, so that we can check it in the XRD. Otherwise, among these phase changing temperature, iron it has been currently with thermographic that iron occur at higher temperatures than any other. Otherwise, the other composition mostly occur in the first reduction occurs between 400 and 500 degrees centigrade. The other is just a conversion efficiency during the redo reaction. So when we see the conversion efficiency, still this is the conversion efficiency for charging temperature. So the conversion efficiency for the normal state, which is in a stable state, still the 50% is in a good and stable conditions out of the other. For example, when you see cobalt, first in the first case up to 400 is okay, it's increasing, but when we come to around 450 and 800 is constant. So when you start 800 degrees, it's sharply increasing, and from 1000 into that it goes to plateau. When compared to iron, it's just the conversion rate is not well converted in this area. So that is the meaning to say. When this is also the conversion, which has to be computed also in the whole cycle of 1 and cyclic 2. It's always see that in the sinusoidal we have for different composition. Still among this occurrence, the 50% by weight manganese percent of cobalt oxide is in a good conversion rate that of the other. It is just in a stable condition. The conversion is just in both cyclic is unstable. So we select this 50% and then we compare the graph, but by weight loss at the same time is conversion within one graph. It is a kind of mirror image, it seems. We see that the main important is the oxygen uptake and the result ratio. That means if it absorbs more oxygen, then it means that the material is in a good way to absorb energy. So when you compare from this table, in cyclic 1 and cyclic 2, the most important thing still we can check that 50%, for example, in the the first cycle is 0.76 in 25-75 composition, 0.98 in the second cycle. When we think 50%, 0.83 and 0.99 is okay. So when you compare all these six composition, still the 50% of weight manganese oxide and 50% of cobalt oxide in a good position for the absorption oxygen, the uptake of oxygen, and the release of oxygen. Okay, so for example, when you think pure manganese oxide, in the first cycle 0.34 is very poor. In the second, it is higher. When you think of iron, it is just higher in the first, in the second also higher. But the main thing that we need is that iron is the main part, but we need the supporting material. When later we are going to be prepared real material as cobalt and manganese to be the supporting material. So which part of proportion of manganese and cobalt oxide is important, as if iron is the central and these are the supporting material. So which proportion of manganese and cobalt is important? The main research work in this condition is selection. Okay. So we also check the phase change condition and conversion. Still, we checked that the phase change condition and then the reduction on say temperature, the 50% still occur on the reduction at 400, as we said before, and the conversion rate for this is 92.34, and a phase changing temperature almost in this region. It has the melting, crystallization, and then this is overall result during the experimental analysis. Still, we checked that this 50% is important in different aspects. We also measured that the energy content, energy density at 950 degrees centigrade. We get different results in cycle 1 and cycle 2. So the main focus out of the other is still the 50% of composition of manganese oxide and cobalt oxide. So in the first is 60.7, the second is 41. So when compared to that of the other, except manganese oxide 24.2 and then 50 points occasional it happen. Otherwise, still the other composition, the 50-50% is in a good track. So conclusion in summary, this study has shown that the proper optimized of energy storage reactor, high oxygen uptake and reserve capability metallic oxides are vital to energy utilization. Materials were selected based on the cyclic stability, oxygen uptake, and during redox reaction. This study utilized for different proportion of manganese oxide, cobalt oxide, iron oxide to produce metallic oxide material, which high thermal energy performances into cyclic redox reaction. Proper mixture of manganese oxide, cobalt oxide can stabilize the weak reaction of rate of manganese and the fast reaction of cobalt oxide, as well as enhance cyclic ability of oxygen uptake ratio. Where when we observe that, and from the theory and from the other research work, that manganese is very weak for the reaction, whereas cobalt is fast for reaction. So the situation of proportion makes the system balance very weak to get normal, very fast to reduce. So the 50-50 proportion is still very important in this work. The combination of 50% of weight of cobalt oxide and that of manganese oxide produce a material with high cyclic stability, high oxygen uptake ratio, and with high energy conversion performance. So from the result that when getting that the 50-50 proportion of manganese and cobalt, when compare with added with iron, so iron made all this the system to more stable, but it was found that it reduced the it was found when it work with. So adding 100% of iron oxide and 50% of cobalt brought the oxide more cyclic stable, but with lower oxygen uptake and release. The proposed solution based on the component of oxide, manganese, and cobalt has a unique feature, which would be an opportunity and alternative material option for high temperature chemical process. Further investigation has to be performed that redox reaction is a wide temperature range requires special approach in adapting structure used in order to achieve high efficient process for uptake release of energy. The effect of pure metallic oxide has an efficient redox process, especially at high temperature, require more detailed and extremely intensive study. Actually, in this work, same state has also done same study, and then mapping also has been done, but this also to indication. Okay, thank you for your listening.
Thank you for your presentation, Dr. Yabibal. So yeah, do we have any questions? Any questions for Dr. Yabibal? Okay, I guess there are no questions. Thanks a lot for your presentation and your time, Doctor.
Okay, thank you. Thank you.
So yeah, moving on to our next presentation. Yeah, moving on to our next presentation, we have Dr. Boshu Jiang from Harbin Institute of Technology, China, on the topic of a CuO-based thermal catalyst for efficient carbon dioxide splitting. Yes, Dr. Boshu Jiang, we can see your screen.
Yeah, can you hear me?
Yeah, we can hear you, but there's a lot of disturbance. Is it possible to just mute the disturbance or anything?
Um, hello, hello. Can you
Yeah,
hear me?
yes, Dr. Jiang.
Yeah. Hello everyone. This is my first time attending an international conference. My name is Boshu Jiang, a PhD candidate working on thermocatalytic development and thermochemical CO2 reduction, mainly using solar energy as a heat source. We have simulated solar simulator and thermochemical reactors, optimized their structure and performance. We also researched the preparation and characterization of thermochemical energy storage materials in depth. We have experts in preparing porous catalytic materials by organic form impregnation method and testing in a thermochemical reactor. The catalyst performance for higher CO2 reduction are improved by different kinds of doping and preparation method. So today I will introduce our research and on the thermochemical reduction of CO2 with copper oxide and nickel ferrite. So this is the outline, and this report contains the following 5 aspects, and 2, 3, 4 is the other results. Now, regarding the atmospheric concentration in CO2 and associated impacts, producing fuels from CO2 is an exciting and attractive perspective for a suitable energy future. In contrast to natural photosynthesis and artificial photosynthesis, using appropriate catalysts could convert CO2 into valuable fuels, which is very in line with the green environmental protection concept advocated by the World today. In this work, the thermochemical cycle performance of copper oxide and nickel ferrite mixed catalysts were studied by thermogravimetric analysis, also known as TJ, based on 2-step thermochemical cycling. Oxygen released in the reduction step and carbon monoxide produced, where carbon dioxide catalyst reduction in the oxidation step of each cycle. And they were measured according to the weight thermochemical cycles. Weight change of sample into consecutive thermochemical cycle, and the crystal structure, latest parameters, surface morphology, and chemical composition were characterized and identified by XRD, ICM, and EDAS. Now, this figure shows the mechanism of the reduction of CO2 and water in a 2-step thermochemical cycle. Hydrogen and carbon monoxide can be produced in the process of water splitting and CO2 reduction. Catalyst redox materials is heated in the first step. Then hydrogen and CO are produced in the second step, where injection of water and or CO2 in the reactor. Although this process can effectively produce the solar fuels, however, finding a catalyst or redox material that can facilitate the process with high efficiency and selectivity, as well as integration into solar conversion device remain the key problems. Therefore, we try to screen out more suitable oxide catalysts by thermographic analysis. In the TG experiment, two thermochemical cycle tests were carried out for each material, and blank tests were conducted to eliminate the influence of carrier gas, buoyancy, and other factors. This is our TG device. And first, we test and compare the cerium dioxide material that was easily available in the paper. And we weighed 15 milligram cerium dioxide and place it in the alumina crucible. The reduction temperature was 1030, and the oxidation temperature was 800, which proved to be a more suitable temperature in subsequent experiments. And the carrier gas in different stages is nitrogen and carbon dioxide with a flow rate of 20 SCCM. We can obtain the oxygen and CO output per gram of material through data analysis and through this and this. It was found that both the amount of oxygen released and the amount of carbon monoxide produced were lower than the data provided in the paper, but the ratio was close, which indicated that the TG experimental measure has a certain accuracy. And then nickel ferrite is a catalyst that we often use for thermochemical experiments, and it has good stability. At the same time, zirconia is a commonly used carrier for preparing porous materials. Therefore, we chose both to test. The experimental setup parameters are the same as those of the previous cerium oxide. It can be seen from the figure that zirconia has no obvious weight change during the whole process. It can be seen that the stability of the carrier is better. By testing different ratios, nickel ferrite and zirconia, it can be seen that the thermochemical reduction of CO2 performance of nickel ferrite is significantly higher than cerium dioxide, like 100 is larger than 50. And 20% nickel ferrite and 80% zirconia can make the unit mass nickel ferrite reduce more CO2. And CO is often used as a catalytic material for electrothermal chemistry and has a strong ability to release oxygen. Then we test the redox performance of CO. The experimental conditions are the same as before. In order to prevent reaction at high temperature, nitrogen in carrier gas is placed with AR. As can be seen from the figure, the CO yield of COO is higher than that of nickel ferrite. But the second cycle is significantly lower than the first cycle, with poor stability. Therefore, it is envisaged to combine the two to get a suitable preparation so that the catalytic material has high stability and high CO yield at the same time. So copper oxide has a good performance of releasing oxygen and absorbing oxygen. So we consider to use COO and nickel ferrite for testing at the same time. The experimental conditions are the same as above. It can be seen that CO has obviously oxygen released at 800 to 900 degree, and the higher the nickel ferrite content, the lower initial temperature of oxygen release. The oxygen release of nickel ferrite is mainly at 1100 to 1300 degree. And by analyzing the experimental data, we can see that 25% CO plus 75 nickel ferrite has the highest CO yield in two cycles and can achieve better stability. So then based on the next analysis of different content on the thermochemical cycle performance, the copper oxide and nickel ferrite was screened and identified as the optimal dopant among the studied materials. Copper oxide is decomposed at from 800 to 900 degrees, so the oxidation temperature is 800. So to ensure the reaction rate and feasibility, for further discussion, the appropriate reduction temperature will be discussed and selected. The oxidation temperature maintained at 800 degrees for an hour, and the reduction temperature vary from 1000 to 1100, and return for an hour too. The heating rate is 20 degrees per minute. The sample mass test was about 11 milligram in a new platinum crucible in each experiment, as shown as in the figure. In the first thermochemical process, the production of oxygen is basically stable at 800 mmol per gram, and the higher reduction the temperature, the more mass is lost. The carbon monoxide production decreases with the increase of reduction temperature. the carbon monoxide production stability of around 150 mmol per gram, and therefore the reduction temperature of 1,300 degree is more appropriate. And to determine the effect of heating rate in the thermochemical cycle, the rate change of 10 to 20, 30 degree per minute we used. Appropriate 13 milligram samples was used in experiment, and as shown in the figure, in the first cycle, oxygen released at 3 heating rates was almost the same, but carbon monoxide production at 20 degree per minute was about twice at 30 degree per minute, and 1.5 times that 10 degree per minute. In second cycle, the carbon monoxide production at 30 degree was significantly lower than the other. Moreover, reoxidation yield in the second cycle of 10 degree per minute and 20 degree per minute is the same. We believe that the reoxidation yield can be maintained and at a higher level at a low heat rate. Then we performed the XRD test on materials before and after heating. This is the after heating XRD. Before heating, they were copper oxide and nickel ferrite, but after heating, they become ferroferric oxide, cuprous oxide, and copper oxide. But the nickel was not analyzed. And this is the ICM imaging of CO and nickel ferrite. It can be seen that CO particles are significantly smaller than nickel ferrite particles. CO adheres to the surface of nickel ferrite particles. This is 25% CO plus 75% nickel ferrite. This part is the same ICM and EDS of the powder. It can be seen that Fe3O4 particles are larger, and CO is dispersed on the surface. Since the stage is a silicon buffer, it is possible that the electron beam has penetrated the material, resulting in a higher silicon content. And this conclusion, CO mixed nickel ferrite thermal catalyst has better CO2 reduction performance compared to a signal catalyst, and CO plus nickel ferrite equal to 1 to 3 has the best performance. The best reduction temperature is 800, and oxidation temperature was 1300. And the catalytic performance of CO and nickel ferrite was enhanced by zirconia to some extent. And then we will use this catalyst to electrochemical test. And that's all. Thank you for listening.
Thank you for your presentation, Dr. Boshujiang. So yeah, do we have any questions? I guess there are no questions. Anyways, thanks a lot for your presentation, Dr. Jiang.
Yes, thanks a lot.
So moving on to our next presentation. Just give me a moment. We have our next presentation from Dr. Goilia Laudico from IMDEA Materials Institute, Spain. So yeah, just let me make you the presenter. Yeah. So
Okay.
now we are going to have the presentation on the topic accelerating development of promising nanocatalyzers assisted by statistical machine learning.
Yeah.
Yeah, it's perfect.
It's perfect? Okay.
Yeah.
Okay. So, hello everybody. My name is Giulia Lodico, a PhD student at IMDEA Materials and Tulsa Company. I work on the implementation of machine learning and data-driven methodologies applied to the design of functional nanomaterials. Today, I talk about an application of those methodologies in a project on accelerating development of promising nanocatalyzers assisted by statistical machine learning. Nanocatalysis attracted the attention of academics and industrials for its advantages such as higher efficiency and higher catalyst recoverability compared to conventional catalytic reactions, and minimal chemical waste involved during the reaction. Typically, nanocatalysis occur at nanoscales and are promoted by active porous nanomaterials possessing higher surface activity. The presence of nanoporosity confers higher surface to volume ratio, allowing the absorption of the reactant at the surfaces and promoting favorable mechanisms. Moreover, the morphology as well as the chemical structure of the surface enhance the selectivity, avoiding the interference effects. Typically, nanocatalyzers may favor the reaction at lower temperature and lower activation energies, and this effect can be illustrated by energy profile diagram, such as the one proposed in figure. Among the natural porous materials, nanoclays are known to be green and low-cost, interesting materials possessing interesting properties that can be employed in nanocatalysis. Their morphology and chemical structure vary depending on the natural environments and deposits, and results in different particle aggregates. For example, palicosite and sepiolite show a fibrous shape, as the one proposed in the top figure, and smectites are known to be layered nanoclays, as the one on the bottom figure. The repeated inverted structure of fibrous clays leads to higher surface area, namely 150-315, compared to smectites, which exhibit around 30-80 of the aluminum-rich ones, and 150-215 for the magnesium-rich ones. Nanoclays typically are critically affected by pervasive substitution in lattice structure and by the exchangeable cations which affect the layer charge and affinity with certain molecules. The structural dissimilarities between various clay structures causes diverse surface activity, which can be approximated in acid-base reaction to Bronsted and Lewis active sites that can be augmented or activated by some modification processes. Here, there are some examples of nanoclays used in nanocatalysis. For example, the catalytic degradation of organic dyes on acid-activated montmorillonites, which allow total mineralization of organic molecules by recyclable clay catalyzers. Then montmorillonites employed in catalytic formation of RNA oligomers, finding evidences of sequence, ratio, and homochiral selectivity of the obtained products. And then fibers of sepiolites modified with zinc oxide nanoparticles tested in photocatalytic degradation of emerging pollutants, such as pharmaceuticals in wastewater treatment. So in this contribution, we want to start from raw clay materials and transform them into acid nanocatalyzers. Typically, the design of nanocatalyzers involves large number of experiments and expensive material characterization. Thus, we aim to accelerate the characterization of processing porous materials and screen a large number of possible modifications, finding the optimal solutions. We address this purpose building machine learning multi-algorithms models and extract the top promising modification treatment, achieving reliable performances. In particular, 6 independent models were built and used for predicting the surface area, pore volume, main pore size, micropore content, and external surface area as morphological targets, and the surface activity in terms of pH, as shown on the leaves of the tree. We fed our tree-based machine learning models, that is the body of the tree, with some information we collected about the raw clay, process treatment, and additives depicted at the roots of the trees. The machine learning model that we implemented is an extra tree regressor after hyperparameter optimization. 2 data sets were employed. One assessing the morphology containing 49 data points, and the second one assessing the surface activity containing 69 data points. The descriptor space were identified by 49 descriptors grouped into 3 main classes: raw clays, additive and process treatment, and the target property were the morphology and the surface activity in terms of pH. Here I disclose individual descriptors. Since the raw clay minerals as natural porous materials are hard to be modeled, the 20 descriptors were experimentally obtained, while the additive were depicted by 14 descriptors obtained by PubChem repository. Then the process treatment, 7 descriptors, identify the different material preparation which can be experimentally made. Then we selected the main features affecting the catalytic performance of clone materials and implement the model prediction proposing the design function shown. Through this design function, we want to screen rapidly the possible modification, finding the best balance between maximizing the surface area while minimizing the micropore content, which is typically not accessible to the substrates, and maximize the surface activity, which in our application means minimizing the surface pH. Then we extracted the top promising modification, and we prepared a prototype and tested in an acid catalyzed thermal degradation of chlorophyll A. Here are resumed the assessment results of our models. Each individual model is trained on the 85% of the data set, and we assess the predictability on the 15% of the data set. Then we compared the prediction with experiments, obtaining the shown plots. Moreover, the table resumes the assessment results in terms of R-squared values, obtaining at least 0.93 of R-squared value for all the models except for the main pore size, which exhibits lower values, likely caused by the approximation of cylindric pore shape, which loses meaning when considered layer clays, enhancing the errors. One of the most interesting abilities of tree-based machine learning model implementation is ranking the features and extracting the most important ones. The main features will drive experimentation, but also provide interesting physicochemical spots for investigation of the effect of the modification in the pristine properties. The figure discloses that surface area, external surface area, and the pore volume are strongly affected by the pristine properties of raw clays, while the micropore content as well as the main pore size are affected by the modification process. These establish a competition between the tendency of the modification of the modifier to the modification of the surface and the tendency to cover it. Go deeper, the raw clay group of features are affected mostly by the phyllosilicate composition and cation exchange capacity, while the octanol water partition coefficient, the molecular weight, and the acid strength are the most important feature in the additive group of features. Then the process treatment are pervasive affected by additive to clay ratio descriptor and the starting humidity. The practical implementation of our approach aims to screen a large number of modification processes, capturing rapidly the effect of the modification on the morphology and surface activity. The ahead maps, even if are hard to to be described gives rapidly a visual guide for experimentation. Each row represents a target property, while the columns are the starting materials which we explored, namely polygorsite, sepiolite, montmorillonite, saponite, and stevensite. We explored just 2 descriptors, which are the main important that we extracted by our machine learning models, reducing the descriptor space. The yellow regions are the improvement areas of the properties, while the dark regions represent a deterioration of the properties. So the dark regions represent the threshold of the structure collapse concurring with micropores formations. Polygorsite and montmorillonite, for example, gets acid character even at low sulfuric acid content, while the SIM treatment falls in conferring significant acid functionalities to the other minerals. And the surface acid was selected as promising additive for the preparation of nanocatalyzers. On the base of the finding extracted by our machine learning models, we designed the function for nanocatalyzer operations, and again, we explored the 2 main features, reducing the descriptor space and the time needed for research. Our proposed design function guides us in screening optimal starting materials as well as optimal humidity and content of additive to be employed. 5 natural minerals with the high purity were explored, namely polygorsite, sepiolite, montmorillonite, saponite, and stevensite. The heat maps represent areas of improvement in red dark, and the improvement or reduction of the design function with respect to the pristine nanomaterials. So as you can see, saponite gets improvements in a wide range of humidity and acid content, while sepiolite is effectively modified up to 5%. The optimum for polygorsite can be extended to 8%, finding the optimal preparation for this material. Similarly, we wanted to assess the role of the impurity contained in natural materials. So 5 stevensites provided by different deposits were used for the test. Those 5 diverse stevensites show a lower impurity from 80% to 60%, named stevensite 1 and stevensite 5. The findings allow us to conclude that the optimum can be generalized for classes of clays, since the optimal regions for low purity stevensite are in the same regions as the high purity one. On the contrary, discrete values suggest that the role of impurity is challenging to assess. Anyway, our machine learning models can capture those differences in compositions, and returns prediction to guide experiments. So our design function was able to identify the top promising materials, processed materials, to be employed in acid nanocatalysis. This was a polygorsite-based materials named P1 and marked in green. We prepared the prototype, we characterized the morphology and the surface activity, and test in an exempling reaction of acid catalyzed thermal degradation of chlorophyll A, finding the 79% of the degradation. A generally accepted mechanism involves replacing of magnesium cations in the chlorophyll A structure with protons at the catalyzer surface, and generally nanocatalyzers achieve 65–75% of degradation. Our P1 prototype improve the performances, achieving 79% of degradation. Finally, we wanted to investigate the transferability of the optimal preparation between different clay materials. We address it. To address it, we explore other prototype based on sepiolite, but fixing the optimum disclosed for P1 for polygorsite. The catalytic activity of P2 indicates no improvement with respect to raw sepiolite or P1, indicating that the findings extracted by our approach are likely not transferable between different classes of materials, remarking the powerful of our design function in screening promising preparations. Our approach was able to cut time and experimental cost for the identification of acid nanocatalyzer, achieving 79% of chlorophyll A degradation and an improvement of around 40% with respect to the pristine polygorsite. Furthermore, the quality of the underlying property models opens the possibility to smart design of other design functions tailored to specific applications. So in conclusions, we have demonstrated an accelerated approach for characterization and development of processed nanoporous materials. We identified through feature importance analysis of the models the main features affecting the properties of processed materials. Each investigate clay based material reveals a unique behavior which is affected by structural defects and ion substitutions. We control the process properties correlation, and we identified the top acid nanocatalyzer, obtaining the 69% of chlorophyll A degradation. Thanks for the attention.
Thank you for your presentation, Dr. Gaelia Lodico. So do we have any questions? Oh, yeah, we do have one question through the chat. What could be the main application of these nanocatalyzers?
Well, thank you for the question, firstly. Our approach was based on search optimal preparation for acid nanocatalyzers. So we selected an example of reaction in the acid thermal degradation of chlorophyll A, while we want to expand the application of those acid nanocatalyzers, finding more reaction in which can be employed the optimal prototypes. We are working on finding some more applications of our nanocatalyzers.
So, yeah, thank you.
Thank you for the question.
So, yeah, do we have any other questions? I guess there are no questions. Thanks a lot. Thank you for your time and your presentation.
Thank you.
Yeah. So as per our schedule right now, we need to go for our lunch, but as it's like we are ahead of schedule today, maybe we can proceed with the next presentation and then we can go for a break for lunch. So I would like to know if Dr. Gangaraju Gedda is ready now, or maybe we can take a break, anything. Dr. Gangaraju, are you online? Okay, sure. Yes, Dr. Gangaraju. So yeah, as you are online, so yeah, thank you for your reply. So yeah, next we'll be having a presentation from Dr. Gangaraju Gedda from Vishnu Institute of Technology, Chennai, India. So this presentation will be on the topic metallic or carbon dot composite as a photocatalyst for water purification, a short review. So, Dr. Gangaraju, we have made you the presenter. Please do click on the screen button just beside the mic and camera so that you will be able to share your screen with us. Yes, Dr. Gangaraju, you can actually click on the screen button so that you'll be able to share your screen with us. Mhm.
Hi.
Yeah, I
Hello.
can hear you now. Yeah, I can hear you.
So to share your screen, ask the organizer.
Yeah, I have. Okay. Yeah, please do click on the screen button. Yeah.
Are you able to see my screen?
Yeah, it's visible.
Is my presentation is visible?
Yeah, it is visible.
Is it full screen now?
Yeah, it is. It is full screen. Yeah. we can start with the presentation, Doctor.
Good afternoon, all of you. So actually for me it's evening, but most of you it might be afternoon. So is my voice is audible?
Yeah, your voice is audible.
So can I continue?
Yeah, we can continue.
Okay. So this is Dr. Gangaraju. So my title was Metallic Carbon Dot Nanocomposite as Photocatalyst for Water Purification. So here I would like to give brief review the current advanced nanocomposites for the photocatalyst that can be purify the water. I am not expert in the catalyst. I am basically working in the nanotechnology for the medical applications. But even though I have interest on this area, that's the reason I participated in this conference. So currently I'm working as associate professor in Department of Chemistry, Vishnu Institute of Technology in India. So let us see what are the water pollutants. So this is our aim to most of the times most of the people are working on the photocatalyst to purify the water. So water is generally contaminated with biological and chemicals. So the biological means it's like microorganisms and also biomedical waste. So which are coming under the biological waste. So similarly, the chemical waste, inorganic pollutants, organic pollutants, inorganic like metals, and also organic like dyes, so which are toxic, and also radioactive compounds. So these are the varieties of pollutant which contaminate the water. So we have to purify this water. So there are a lot of the research ongoing for the water purification, which is emerging area. So let us see what is the photocatalyst. So what is this role? So how it is purifying? So it is the photocatalyst substance that can enhance the chemical reaction in the presence of source of light. So in the diagram we can see that we are using the UV light in the presence of the photocatalyst. So that photocatalyst reacted with the light, and it will be degrade the components which are present in the water that can be purified. So we will try to understand more details in the later. So let us try to understand the natural photocatalyst is that plant leaves. So the plant leaves containing the chlorophyll, that chlorophyll absorbs the light source from the sunlight. It converted water and carbon dioxide into oxygen, glucose. So the plant leaf is the best natural photocatalyst. So there are varieties of photocatalyst they established by using the sunlight and also UV light, some visible lights. So this photocatalyst is also doing the same principle what the plant leaves are doing. So they will reacted with sunlight and they will create some reactive oxygen holes. So those will be effect on the degradation of the pollutants. So let us see that here is the principle how the photocatalyst is working. So the photocatalyst, when it is reacted with the light radiation like UV light, gamma rays, X-rays, or visible light, NRA radiation, when they are reacted with the light, so the electrons will be jump from conduction band to valence band. So there they will create the holes, and also the excited electrons reacted with environmental atmospheric oxygen, they will create it react to oxygens and also hydroxides. So this hole will be reacted with. So when the electron is jumped from the valence band to conduction band, it will create the hole. So this whole will be reacted with the water molecule. Then it is converted to the hydroxyls. So these hydroxyls and also react to oxygen species, which will be degrade the pollutants which are presented on the water. So here we can see the simple mechanism that traditionally using the photocatalyst, that is the TiO2. So it's the band gap is 3.32. This band gap is most important in this photocatalyst. Based on this band gap, it will be decide the suitability of the light. So most of the TiO2s, they are suitable to the ultraviolet light. So when we are reacted with ultraviolet light, so first we have to mix this TiO2 with the condensed water. So then we will treat it with the light. So after during the treatment, so the photocatalyst, it will be generate the reactive oxygen and hydroxyls. Those will be degrade the pollutants. So finally we will get the purified water. So why the nanoparticles? So in the previous section also, the professor is explained most details about the nanometer based catalyst. So these nanometers are, the size is very less. Because of size, the surface area is increasing, and also shape and size of the materials will be affect on the photocatalyst. The absorption potential is very high. So that's the reason the nanometers are more effective photocatalyst for the treatment. So here is some various kinds of examples which are commonly using photocatalyst in the water purification. So, but there are varieties of materials, nanomaterials using for the photocatalyst. But even though there are some limitations, the major limitation is that the band gap is very less, very high. Because of that, it is unable to use the natural radiation, that is sun rays. So it can be only used 3%. And also most of the photocatalyst experiments performed under the UV light. So it is very dangerous for the human being. So that is, these are the major disadvantages in the nanometer based photocatalyst. So then alternative, it's very important to use visible light and also NRI light. So the visible light and NRI lights are not harmful, and also it's the NRI light is using in the biomedical for the depth penetration of the treatments. So if we can prepare the material that can be effectively work under visible light and also NRI lights, much better. So the carbon dots are best alternative. So for to resolve this problem, so the carbon dot based nanocomposites means that first we will prepare the nanomaterials combination with the carbon dots. Though these nanocomposites will be decrease the band gap, so that's the reason we can use varieties of the light source, even the household light, NRI light, visible light. So this carbon dot based nanocomposites can be the better alternative for the traditional based nano catalyst. So let us see what are the carbon dots when they are investigated. So these carbon dots are very small size. The size is less than 10 nanometers. So these carbon dots are investigated during the single wall carbon nanotube purification. It was investigated by Zhu et al. In 2004. So various kinds of natural sources and bio waste are converted for the carbon dioxide. So for the preparation of the carbon dioxide, it does not require any additional precursors or chemicals. So the natural source can be the precursors. So that's the reason the researchers attracting more towards the carbon dots. So these carbon dots widely applied in the biomedical applications. So recently the people is also focusing to explore the photocatalytic properties, efficiency of these carbon dots. So these are the general approaches for the preparation of the carbon dots. So there are basically top down, bottom up. In the top-down, laser ablation, ultrasound, and electrochemicals. These are the generally using methods for the preparation of the carbon dots. In the bottom-up, microwave, thermal decomposition, ultrasound, and hydrothermal. So these are the basic techniques which converting the natural source into the carbon dots. So these materials shows varieties of properties like surface functionalization, fluorescence, solubility, inertness, non-toxicity, biocompatibility. So because of these materials, it's widely applied in bioimaging, biosensor, drug delivery, antimicrobial agent, photocatalyst, nanomedicines. Specifically, the more interesting, these carbon dots also used as a photocatalyst for the degradation of the dyes like methylene orange, methylene blue, and also water splitting, and some of the photocatalytic organic reactions and CO2 conversion. So the researcher already started to investigate the photocatalytic efficiency of the carbon dots. But there is the one disadvantage that the carbon dot alone, it's showing the very, very low efficiency. So if we can improve this efficiency, so that will be the better and a unique photocatalyst. So before the carbon dot as a photocatalyst, we discussed about the nanomaterial as the catalyst. It means that metal-based nanomaterials. So the metal-based nanomaterial mostly it is using the UV light. So here the carbon dots people are using the visible light also, but the efficiency is low. So if we can prepare some composites, that is the carbon dot based nanocomposites. So the carbon dot based nanocomposites can be more efficient for the treatment of water purification. So here are the steps for the preparation of the carbon dot based nanocatalyst. So generally for the preparation of the carbon dots, we will take varieties of the carbon, bulk carbons like graphene, carbon sheet, like that, and also small organic molecules, natural sources, and synthetic polymers. We will prepare the carbon dot from those, and also we use the metal sulfide, metal oxides. So these are the nanomaterial precursors. So we use carbon dot and also metal composite for the preparation. That is the one part or multi steps. So after the preparation of this nanocomposite, we use as the photocatalytic degradation of the organic pollutants or biopollutants. So here is the mechanism or methodology. So as we discussed in the previous discussion, we use the natural or synthetic precursors for the preparation of the carbon dots by using the bottom up and top down. Same time we will take the metal precursors. So that will form the nanocomposite. So this nanocomposite we will treat it with either NRI or visible light. So they will be create the reactive oxygens and the radicals. So those radicals, it will be degrade the contaminated which are presented in the water. So this is the formation of the metal carbon dot nanocomposites. So initially we will take some natural precursor. Here we will use the neem leaf. So we will convert it to the powder, and we use the hydrothermal method. So there are the other methods also. We can also use microwave, ultrasonication, electrochemical methods for the preparation of the carbon dots. So the formed carbon dots, its surface having the varieties of the functional groups like hydroxide, amines, COH functional groups. So those functional groups reduce the metal precursors. So here we can see that the carbon dots itself working as the reducing agent for the formation of the metal carbon nanocomposite. So this is the another uniqueness of these carbon dots. So most of the metal nanomaterial, they use the varieties of the organic, some of the kind of reducing agents. So here we does not require any reducing agent. We does not require any protecting agent. So this is the most unique advantages of the carbon dots. So here we can see this carbon dot act as a reducing agent for the metals and protecting agent to avoid the agglomeration, and also capping agent, and it's improve the water solubility and facilitate the surface functional groups and enhancing the photocatalytic activity. So these are the some of the photocatalysts currently used for the photocatalyst applications. So one is that copper carbon dots, which are prepared by the pyrolysis method, and also nitrogen doped carbon dots, iron oxide carbon nanocomposites, and carbon dots silica oxide, and carbon dioxide silver nanocomposites. So these are the few of the examples which already established for the photocatalytic applications. So here we can see that the mechanism of what is happening. So the first figure, it is the metal nanocatalyst. So here the metal nanocatalyst, because of the wide band gap, we are using the UV light. So when we are using the carbon dots, so NRA light absorbance, so we can use that NRA light absorbance and also the nanocomposites with the CDS. So the uniqueness is the carbon dots, when we are able to prepare to absorb visible light and NRL light, so those can be create the holes and oxygen radicals and hydrogen radicals. Those will be will degrade the pollutants. So here is our ongoing experiment. We are using that titanium oxide carbon nanocomposites. So we also observed that the degradation, we are not showing much details here, results. So from the initially it is the dye. So upon the increasing the catalyst concentration, we can see that completely degradation from the 1 to 10. So if we can prepare the better nanocomposite, that is the carbon dot with metals, can be the best alternative for this water purification. So there are the varieties, few of the nanocomposites carbon based already developed, but there are some limitations. That's the carbon dots alone, it shows very low photocatalytic efficiency compared to the nanocomposites. So it's required the systematic study like carbon dots, sizes, and other physical properties, chemical properties, how they are affecting on the photocatalytic efficiency. So most of the literature currently it is more targeted only the few dyes, that is methylene blue and methyl orange dyes in the pure water. That is also they are not using the real time water. They use the pure water dyes methylene blue and methyl orange. So the real world problem is very important. So it's important to focus the nanocomposites in the real time water degradation, for the degradation of the pesticides in river water, lake water, and so on. So there is still the opportunity to prepare the better nanocomposites. So I also believe that we can prepare the bimetallic and trimetallic. They may be show more efficiency. So I am acknowledged to my co-workers, Dr. Arvind Kumar and Sivakumar, principal and professor in Gautam University, and Professor Ufen Wu in Taiwan, and Krishna Kanti from the Gautam University, Surbabu Joga, he is my colleague, Vishnu Institute of Technology, and TVL Balaji Gupta, he is also my colleague. So please contact us if anyone interested to collaboration with work together. So here is my email address. Thank you to all. So let us know any question and answers.
Yeah, thank you for your presentation, Dr. Gangaraju. So yeah, do we have any questions?
I think there is one question.
Yeah. Do not dead microbes pollute water anymore? I mean, are they not harmful to human health anymore?
Yeah, microbials also harmful. So that's why we have to prepare the better on catalyst, because this carbon dioxide nanocompounds so far they've only tried on the dyes. So we have to check with the microbes also.
Okay. So, yeah. So the catalysts need to degrade microbes too.
Yes. Actually, that's the reason first initial slide I kept that different kinds of the cattle pollutants, biological and chemical, both all the things we have to use by using the UV visible light and NRI light.
Okay, thank you. So, any other questions? I guess there are no questions. So, yeah, thanks. So, thanks a lot for your presentation and your time. So, we are left with two presentations, and yeah, we'll just go for a short break and we'll come back at 1:30 p.m. So, yeah, I hope everyone joins back at 1:30. So, as we are ahead of the schedule, we'll be starting up our schedule with Dr. Anirudh Bahadur Yadav from India. So, and later we'll have the presentation from Dr. Pragati Sukla. So, yeah, thank you. We'll meet back at 1:30.